So let's continue. Yeah. Now we need to find some algorithm that does not rely on prime factorization, very expensive operation. Yeah. All right. So method number 2. Yeah. We need to use a different property. Yeah. So our goal, yeah, reduce the problem size. Yeah. When we work on GCD problem with smaller problem sizes, not that hard. Okay. Yeah. So the question is, can we find a way to reduce the problem sizes? Yeah. All right. Yeah. All right. There is a mathematical tool we need to use to solve this problem. Yeah. So what's that tool? Division algorithm. Yeah. It's a very simple division. Everybody knows how to do division, right? Yeah. Integer division. Here, the division we use here, integer division. Yeah. So for the integer division, yeah, so we can write the algorithm explicitly here. Yeah. Very simple. Given positive integers a and b, because we need to use b as the divisor. Yeah. So that's why we require that b cannot be 0. Yeah. Divisor cannot be 0. Okay? A could be 0. Yeah. All right. Then there exist unique integers q and r. Q for quotient, R for remainder. Yeah. Q and R with R in the range between 0 and b. 0 is inclusive, but the b side exclusive. Yeah. Exclude, because our remainder cannot be equal to the divisor. Yeah. Otherwise, if the remainder equals divisor, then you can change the quotient number plus 1, right? Yeah. Because you can move, the extra more part, you move to the quotient. Yeah. If R equals B. Yeah. So for that reason, you can assume the remainder must be strictly less than the divisor number. Then we can write formula, yeah, integer division formula. Yeah. A equals B times Q plus R. Yeah. Very simple, right? Yeah. So simple. Yeah. But this is a basic method we call it division algorithm, and it is very important in number theory. So this simple result, so simple, but it is very fundamental in number theory. Yeah. All right. So now we need to use this mathematical tool to help us do this, reduce the problem size. All right. Yeah. So now we, in our current problem, so when we apply this division algorithm, yeah, so A corresponds to n, yeah. B divisor, yeah. So our n, we use n as the divisor, yeah. Then we need to, find appropriate corresponding quotient number and R number. But actually here, the R number is important, the quotient number is not important. Okay? How large is the quotient? It's not important. Yeah. How large is the remainder? It is important. Okay? Yeah. Yeah. Because the quotient part we will throw away. Yeah. We don't need the quotient part. Yeah. Throw it away. Yeah. All right. Yeah. And where we consider the general problem, we do not require which one is larger, which one is smaller, right? M larger or n larger. We do not have any requirement Yeah. But when we implement our new algorithm for convenience, we like to make m greater or equal to n. Yeah, because that's the meaningful case. Yeah, because in that way, you know, when we do division like this, we can, you know, get a smaller R number, right? Yeah. Otherwise, if you do the other way around, you know, not meaningful, right? Yeah, think about it. So if you switch, if you make, you know, smaller n number, n equals q m plus r, but your n is smaller than n. In that case, the q is 0, right? The q is 0. Then your r equals n. Yeah. Your r equals n. Then your operation is meaningful. Not meaningful. Wasted, right? Meaningless. Wasted. Yeah. So for that reason, then we make this assumption. Okay? In order to avoid that meaningless case. In this case, your calculation is, you know, wasted, because you do not get any helpful information from this operation. Okay? So for that reason, we want to make our algorithm, you know, meaningful all the time. Yeah. So we make this requirement. Yeah. In your implementation, you can do that easily, right? You swap. Yeah. Because we know GCD m comma n always equal to GCD n comma m, right? So it will swap these two parameters, you get the same answer. Yeah, so then you can always do swapping to make the larger parameter as the first parameter, smaller parameter as the second parameter. Yeah? Yeah. All right, yeah, after that treatment, so now let us look at the size reduction issue here. Yeah. So then we write this apply division algorithm directly. Yeah. All right. After that, then we want to see how to bring down the problem size. Yeah. So that's our key question. Yeah. So we need to develop a key property here. Okay. All right. Through transformation. Now we need to do formula transformation. Yeah. Yeah. All right. So now we need to consider some special operation related to the common divisor operation. Common divisor related operations. Yeah. All right. Yeah. So GCD of these two numbers. For the first parameter n, we have a new expression, right? Yeah. By the integer division or division algorithm, we have a new expression. Yeah. Right hand side, new expression at the right hand side. Yeah. Let us replace n by nq plus r. Okay. All right. After this one-step transformation, you can see the first term, it's a multiple of n. Yeah. Q times n, it's a multiple of the second parameter. Yeah. This property, we need to take advantage of it. Yeah. So let's see, how do we take advantage of this property? Yeah. All right. Let us do, we know here, in order to consider the common divisor question, yeah, here we use the fractional form to, consider the common divisor question. All right. So in this fractional form, yeah, because we apply this integer division, yeah, Qn plus R over n. After simplification, we can write the quotient part, yeah, quotient, the first term. After you do cancellation, n numerator and denominator, and you do cancellation, so you have an integer q term, yeah, and after that you have a remainder over the divisor term, yeah. But this integer term, the first term, integer term, it does not impact the second fractional term, right? Yeah. The integer term could be large, small, the q could be any number, but whatever the number q takes, the second fractional form, the common divisor of the second fractional form, has nothing to do with the first integer number, right? Yeah. Based on that observation, so we do not need to look at the q, okay? Yeah. If q is 3, 4, 100, it doesn't matter, okay? Yeah. So based on this observation, you can see the common divisor between m and n is the same as the common divisor between r and n, right? That observation, okay? Yeah. So based on that key observation, now we can do simplification. So this nq term we can cross out, okay? Because it does not change anything related to the common divisor of m and n. So that's the key observation, key property, okay? Then that means we can simplify the GCD representation, yeah? So we drop that nq term, then we have Rn. Remember, we swap two parameters to make the first parameter greater than the second parameter for convenience, okay? For further integer division applications, okay? Yeah, because we need to apply the division algorithm second round, third round, and keep doing that division algorithms until we reach the end, right? So we have to stop somewhere. We cannot do it forever. Yeah. Yeah. Because you do size reduction and eventually you have to stop. Okay? Yeah. Eventually you get to some point, then you can stop. Yeah. But we need to examine that stopping condition. Yeah. All right. Yeah. But the good thing is, when you look at the transformation we are doing here, you can see, yeah, the first expression, the problem size larger. The second expression, now you can see the size, the overall size. Yeah. So here you may ask me, how do you define the problem size of GCD problem, right? Yeah. How do you define the problem size? How about the maximum, so the magnitude of the larger parameter, how about that? We use that to, the maximum, yeah? Because m and n, one is larger, but we like to use the larger number, right? Yeah. But the magnitude of that larger number we use to define the problem size. Okay, all right. Yeah. In that way, you can see, yeah, so you bring down the problem size. Yeah. Yeah. All right. And this is special size reduction way. It is a variable size reduction. Yeah. Sometimes larger, sometimes smaller, yeah. And it's hard to predict. Yeah. How to predict how large you can bring down the problem size. Yeah. 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 All right. Next, yeah, we need to, so at this point, so this is our key formula. So here, yeah, so we derive the key formula. Okay. Next, we will apply this formula. Yeah. Here you can see the formula recursion, right? Yeah. Yeah. So matches our topic of this module, recursive algorithm. So you can write your algorithm based on recursions. Yeah. All right. So next, that's the Euclid's algorithm. Okay. The famous Euclid's algorithm. Right. The rule, yeah, so we need to, look at the rules. Yeah. To evaluate the GCD function on two variables, yeah, yeah. First, yeah, the trivial cases, the first two cases, the trivial cases. Yeah. So when y equals 0, then you just return your function, GCD function returns x value. But you need to make sure x, check the value, x cannot be 0. Yeah. If x happens to be 0, you have to output an error message. Remember, yeah, the error message, yeah, GCD of 0 and 0 is not defined. Yeah, so you need to tell your users, yeah, it's an error. Okay, yeah. So this operation is not defined. Yeah. All right. Otherwise, yeah, you return x. All right. Yeah. Then, under what situation you return y? When x mod y. Yeah. This percent sign, we know it's the mod operation, right? So in a typical high-level programming language, people use it as the mod operation. Yeah. If the remainder equals 0, that means x is a multiple of y, then you just return y value. Yeah. Yeah? So y value. Yeah. That's easy to see. Yeah. All right. Third case, otherwise, yeah, you calculate this is the remainder, but you need to swap the two parameters. Yeah, you need to put the divisor as the first parameter, remainder as the second parameter. Recursive function call. Yeah, you bring down the sizes. Right. All right. Then, so if you call this function recursively, sooner or later. Remember, we talked about the termination condition before, yeah, or stopping condition before. Yeah. Eventually, you will get to the second case. Yeah. Second case. Yeah. The first parameter happens to be the integer multiple of the second parameter. Sooner or later, you will get there. Then you stop. Okay? Yeah. Yeah. All right. So now you can see this is a new algorithm to find a GCD. And in this algorithm, you do not need to do prime factorization. So the basic operation you use, actually, it's the modular operation. You do division, and you keep the remainder. You throw away the quotient. You just keep the remainder. That operation, very cheap, right? Yeah, very fast, very fast. Yeah, modular operation. So here you can see what's the improvement. The improvement is from prime factorization, very expensive. The main change reduced to modular operation. Modular operations. Okay? Yeah. And the modular operation extremely fast. Yeah. Extremely fast. Although you can argue, people can argue, so for the prime fraction, we only need to do 2, but modular operation, you need to do many, right? Yeah, yeah. Even that, still much, much faster. Yeah. Because not just 2, you even do 1 prime factorization for a huge number, thousands of digits, huge number, you need, months or years. That much time, that level, okay? Yeah. So comparing with that, so your modular operation is much, much faster. Yeah. All right. So now we complete. Yeah. So here you can see. Yeah. This is Euclid's algorithm. Okay. Yeah. Yeah. More than 2,000 years old. Okay. 2,000 years old. That old. Yeah. All right. Yeah. All right. Before I go to the next topic, I want to, because this topic related to our programming project number 2. Okay. Now you can see, 2 methods, right? Yeah. Okay. Yeah. First method, GCD. Calculate GCD. The first method 1, prime factorization. This primary, remember our module 1, right? Module 1, part B. Okay. Yeah. Then method 2, compare Euclid. Okay. All right. So in this question, this project, you need to implement these 2 algorithms. Okay. Then you compare. Okay. But when you do comparisons, you need to apply on relatively big integers. But I do not ask you to, work on large integers with thousands of digits. That's too slow. Okay. Yeah. So you choose appropriate size. Okay. Yeah. It takes relatively long time, but you can tolerate, right? You can tolerate at least. Yeah. So not too slow. So you choose appropriate sizes of your parameters. Yeah. Yeah. So the worst here, the longest time you can wait, probably several minutes. Okay. Yeah. Even within a minute. Yeah. I'm fine with your sizes, so you can find the GCD values within 1 minute. Okay, yeah, within 1 minute, not too long. Okay, yeah, 10 seconds, 20 seconds, also fine. Yeah, yeah, 10 seconds, 20 seconds, because we already know it's very slow. Okay, we already know it's very slow. Yeah, yeah. Then the GCD, I think, fraction of second. Okay. Certain number of milliseconds, extremely fast. Okay, I just want you to compare how big is the difference in algorithm efficiencies. Yeah. So that's our project number 2. Okay, all right. So, still on Saturday I will post the project. Okay, project description this Saturday, so I will make it available in Canvas. Yeah. All right. So, but you still need to complete your homework assignment first. Yeah. Yeah. All right. So that's the BPON 2 topic. Yeah. Next, we move to our part C, Fibonacci numbers. C.1, Introduction to Fibonacci numbers. Yeah. In this topic, we have another interesting idea regarding algorithms we can learn. Yeah. So let me explain. Yeah. The question is very simple. Yeah. I think most of you heard of this famous Fibonacci numbers. Yeah. So the definition based on this recursion formula. So very simple recursion formula. Yeah. Two base numbers, f0 equals 0, f1 equals 1. Yeah. So the reason we need two base numbers, not one base numbers, because the recursive formula is the second order recursive. Remember I explained the first order, second order. Second order recurrence rate. First order, when we work on the problem, puzzle problem, Tower of Hanoi problem, that's the first order recursive formula. Yeah. So this place, second order, so you need two base conditions. One is not enough. Okay? One base condition not enough. Yeah. All right. So f sub n equals fn minus 1 plus fn minus 2. Yeah. Here, how do we see the degree? Yeah, remember? Yeah. So left-hand side, the subscript n. Right-hand side, let's look at the smallest subscript. Then we take the difference of these two numbers. Yeah. So that is the order of the recurrence relation. Yeah. All right. So with this simple recurrence relation, yeah, very simple, yeah. And in this way, you can calculate the famous Fibonacci numbers. Yeah. All right, find the Fibonacci numbers. Yeah. Given the input value, the subscript input value, you need to, your function, you need to calculate the capital F, the Fibonacci numbers. Yeah. For the first few, here you can see, these are the first few Fibonacci numbers. Okay? Yeah. Yeah. All right. Yeah. So the next question, we need to calculate it. Yeah. So we need to make a plan. So how do we calculate? Yeah. There are many ways to calculate. Yeah. All right. One way we solve it algorithmically. We can write an algorithm. We can write a code to calculate these numbers. Yeah, that's the first way. Yeah. But the second way, yeah. So we will see that. Solve it mathematically. Math formula. Can we derive a formula to represent this capital F function? Yeah. So if we can find a formula, we just plug in the input number, so then we just calculate the value of the function, yeah, directly. Yeah. So that's different from the first way, using computer algorithms. Yeah. Two different ways. Yeah. All right. The first way, let's look at a simple implementation. Well, because given the recurrence relation, we already have the recurrence relation. So we do not need to derive it. It is given. Now, if it is given, we can write the recurrence relation. We can write its implementation directly like this, right? Just a few lines. Okay? Yeah. All right. But the question is, after you have the implementation of this algorithm, you need to ask question. Yeah. Is it a good one? How good it is? Yeah. If it is not good one, can we improve it? Can we make it better? Right? Yeah. So we need to consider that question. Yeah. So you should not be satisfied on the correct results, right? Yeah. So yeah. Some people, so if they are satisfied with the correct results, yeah, after you get a computer algorithm training, we know the computation time is very important. If you need to wait long time to get correct answers, then it's too late, too expensive at least. Yeah. From the computer resource point of view, it is too expensive. You use too much precious computing time. Yeah. That's not good. Okay. So we want to save computation time. Yeah. So we want to see if the simple implementation can give us very fast computation result. Okay, all right. Yeah. How to see it? Yeah. Yeah. All right. Yeah. How to see it? Yeah. All right. We need to look at that. Yeah. So here I give you the answer. It's a horrible implementation. That means extremely slow. Yeah. 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 How slow? Yeah. Extremely slow. Okay. Yeah. You know. Exponentially slow. Yeah. Exponentially slow. That means the efficiency function is an exponential function. Exponential function. We know exponential function very slow, right? Yeah. Very slow. But this one, that's slow. Okay? Exponential function. That's slow. Yeah. Why? How do you see that? Yeah. So let's see why it is so slow. Okay? All right. Here I show you a simple example. Try to see why it is so slow. Yeah. All right. Here, let me draw a recursion tree. Yeah. Because when you do recursion, you need to calculate a sequence of numbers in certain order, right? Yeah. So here we use a recursion tree to visually understand what are those intermediate results we need to calculate. Yeah. Here I use a small number, Fibonacci of 6. Yeah. It's a small number. Yeah. So at the beginning, yeah, the input is 6, yeah, small number. So we want to see, in order to calculate Fibo of 6, yeah, how many intermediate temporary numbers we need to calculate. Okay, all right. First, you need to know Fibo of 4 and a Fibo of 5, right? Yeah, yeah. These two intermediate numbers you need to know. Yeah, but they are not given, right? Yeah, because from the base number you only have Fibo of 0, Fibo of 1 given. Yeah. Fibo of 4, Fibo of 5 not given. So if it's not given, then remember in our Monday's class, we push these two numbers into the stack, right? Push into the stack. We hold, yeah, we will delay our calculation of these two numbers. Yeah. Yeah. All right, we use a stack to do the implementation. After that, yeah, in order to get a Fibo of 5, you need to know Fibo of 4 and a Fibo of 3. Yeah. But they are not given, so you push them into the stack again. Yeah. Similarly, yeah, for 504, you need to do the same thing, right? Yeah. So that's why you can draw a recursion tree. Yeah. So you need to, you know, branch to many intermediate numbers. Yeah. All right. Yeah. You keep doing until you reach the bottom. When you reach the bottom, you get the two base cases here, because two base cases are given. Yeah. You know, then you can do the calculation. Yeah. So you have the values, so you can find the, you know, other values. Yeah. But here you can see, in order to find the value of 5 of 6, you need to store all these intermediate results in your stack. Here. Can you see any problem here? Yeah. In your stack. So that's how much information you need to hold in your stack of the recursion. Okay? Yeah. Yeah. And you can also see you have a lot of redundant data, right? Yeah. Because some numbers repeated many, many times. And those repeated numbers, you can see, yeah, a lot of redundancy, right? Yeah. So here you can see for fiber of 2, how many times we repeat fiber of 2? Okay? Yeah. Here, you just see a small example. You can imagine when this input number is large, how much redundancy you may have in your implementation. Yeah. Huge amount of redundancy. Huge amount of redundancy. Okay? All right. So that's the reason you have exponential efficiency function. Extremely slow. Yeah. All right. So now we understand why our first implementation is horrible. Okay? Useless. Yeah. Useless. Yeah. Yeah. All right. Yeah. But the next question, we want to improve it. We want to remove the redundancy to make it useful. Yeah. After the modification, then we will make it very fast. Yeah. It is useful. Yeah. People can use it. Yeah. So that's our next step. Right. How to improve the algorithm? Yeah. Method 1. Yeah. Method 1. Yeah. All right. Iterative method algorithm. Yeah. Iterative. We do not use recursion. Remember? Yeah. In our first class of Module 3 discussion, yeah, we have a non-recursion version. It's iterative method. Yeah. In that method, you can see we just use a for loop. Yeah. We start with 2 base case numbers. Then in our for loop, we just do straightforward for loop implementation. Yeah. Also very simple. Yeah. Yeah. Also very simple, but we can find the correct answer quickly, right? Yeah. You know, that's for loop. Yeah. You can see no redundant calculation, right? Yeah. That's for loop, you know. Yeah. No redundant calculation. Yeah. Why no redundant calculation? Here, let me quickly show you why no redundant calculation. Okay, all right. The first, yeah, because here we calculate F array, so our data, F array, in order. Yeah. The first unknown f number, we calculate f of 2, right? Yeah. The second, f of 3, because in our for loop, we calculate in that order, right? Yeah. Last one, f of n. Yeah. And here you can see each f number we only calculate once, never more than once. That means no redundancy, right? Yeah. But in our previous algorithm, yeah, each intermediate f number we calculate more than once, right? Yeah, large number. Okay. So here you can see the first method, we use a simple for loop. We can eliminate all the redundant calculation. Yeah. So that means this algorithm should be very fast. Very, very fast. Yeah. If we use our asymptotic notation, remember our module 2, yeah, we learn asymptotic notation. Yeah. Because when we want to represent how fast is the algorithm, the best way is using our asymptotic notation. Yeah. Here we can use big O of n, yeah, or big theta of n, right? Yeah. Yeah. Big theta of n. Yeah. Yeah. Because when we talk about algorithm, most of the time we are interested in the upper bound. So most of the time people not very interested about the lower bound. Yeah. Only upper bound. So for that reason, people frequently use the big O notation. Because big O notation, we don't look at the lower bound. We only look at the upper bound. Yeah. Yeah. Big theta, although it is more accurate than big O notation, yeah, but not necessary, right? Yeah. So most people, yeah, because they do not need to deal with the lower bound. Yeah. Yeah. Although it gives more information than big O notation. Yeah. All right. So now you can see we already have a much better improvement. Yeah. 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 So if you compare with the older one, the previous one, the horrible one, that one, I can also use the big O notation, asymptotic notation. It's an exponential function here. What exponential function? So I can give you that one. Phi to the n. It's an exponential function. What's this phi? Phi is the golden ratio. Golden ratio. So we will learn this golden ratio quickly. Yeah. Famous number, golden ratio number. Okay? Yeah. That's the phi number. Yeah. The base of the exponential function is phi. Yeah. So how do you get that phi? Yeah. So the remaining of the module 3, we will see it. Yeah. Why Fibonacci numbers are closely related to the golden ratio number. Yeah. All right. Method 2. Yeah. So there is another method. Yeah. Another method. The implementation idea is completely different from the method 1. Yeah. So let me use the remaining of this class to explain method number 2. Yeah. The idea is very important. In computer algorithms, this idea is extremely important. Yeah. Yeah. All right. So this improvement idea, actually, it's a very important idea in this module. Module 3, recursive algorithm. So this idea, implementation idea, yeah, very valuable. Yeah. So let me talk about that. Right. Because our goal, we want to write a recursive algorithm implementation without redundant computation. Here the difference, you can compare the difference with the first one. The first one, we avoid recursion directly. So we don't have anything about recursion. But the method 2, we still we keep the recursion. We do not throw away the recursion. Okay? We still keep the recursion. But we do modification. We apply the recursion carefully. When we apply the recursion, we avoid, we eliminate so redundant computation. That's the idea. The question, how do you avoid? How to eliminate all the redundant calculation? That's the valuable idea I want to introduce to you. All right. Use an array to store the calculated values. Intermediate. Because we need to store many intermediate values, right? So those values, we use one special array to store. This is the key idea. So this is the key idea of this implementation approach. All right. Make sure that no value is calculated more than once. So that's the way we avoid redundancy. See, more than once. This big idea, there is a title for it, dynamic programming. That's the dynamic programming idea. It's a big, important idea in algorithm. It's a topic in chapter 8. So very late in our textbook. And actually, this dynamic program topic, it's a graduate level topic. So it's not an undergraduate level topic. It's a graduate level topic. Okay? But because it is so useful, so important. So here I give you a simple introduction. So we will not go very deep in this dynamic programming, but I just give you a very simple introduction to this topic in our method number 2. So you can see the implementation, so simple. Just a few lines. We can avoid all the redundant calculation. But the idea is big. All right? So let me talk about the essence of the idea. What's the essence? No repeated calculation. So this is a high level idea. But how? How to do it? That's important. How to make it happen? That is important. So let me show you. The working details, so simple, so straightforward. So it's not a magic. It's not magic. And very straightforward. All right. So, Method 2, dynamic programming. We still do the recursion, but when we do the recursion, we will do some careful treatment on our data. So we will add some special careful treatment in our data maintenance, management, data management. All right. So the method, another method for another name for the dynamic program, people also call it dictionary method. What's the dictionary? You need to create a dictionary to store your intermediate results. It's a dictionary. Why we call it a dictionary? Because we can look up. We can look up the intermediate values in our special dictionary. Okay? So that idea, you can see, pretty simple. But your intermediate results can be looked up. Okay? Our first horrible method, those intermediate results cannot be looked up, right? So now you can see what is the improvement. If you can look up your intermediate results, then you can avoid redundancy. if you cannot look up your intermediate results, you need to repeatedly calculate those same intermediate results again and again. That's the reason you waste your computing resource. Now you need to carefully maintain your intermediate results in a dictionary. When you can look up your intermediate results, then your algorithm suddenly becomes very efficient. That's the essence of this idea, this brilliant idea. All right, let me show you basic properties of this method. All right, so here, this is also a good thing. We can keep our recursive algorithm. We do not throw away our recursion idea. Because the whole recursion idea also very valuable because it is very powerful. We know recursion method, recursive algorithms, very powerful. We don't want to throw away the power, right? Nobody wants to throw away its power. So we want to keep its power. So that's why you need to do the recursion. But we can use dictionary to store. So here we need to create dictionary. You may ask me, what's the dictionary, right? What's the dictionary? So dictionary, not fancy. Here our dictionary is just basic, an array. We use an array as a dictionary. That's simple. Okay, all right. All right, So then, this is implementation. Still recursive implementation. All right. So then, here you can see, this line is checking. Okay. How do you make sure no value is calculated more than once? This is the line, the checking line, to make sure. Because here we create a special array called a non-F array. From the name you can see, if the value is greater than 0, then the value is known. It's meaning. Because we initialize this array with all the elements 0 value. Okay? If an element has the 0 value, then we know its corresponding Fibonacci number is unknown because we never calculate it. We never calculate that Fibonacci number. It is unknown. So 0 means unknown. Non-zero means known. Okay? So that simple property. So we use this line, we can check. If it is known that no calculation on that Fibonacci number, you return the known number, right? So this is the lookup step, dictionary lookup step. What do you mean lookup? Because you check this value positive, that means you find it in the dictionary. You already find that Fibonacci number in the dictionary, then just return it. That's simple. No calculation, just return it. That's why it avoids redundant calculation in this way. All right. Then, so then 2 base cases. Okay. After that, all right, then you do the calculation by the recursive formula. You can see. So here we don't worry about the recursive function call. We still do the recursive function call. Okay. All right. But when we get a value, we store it in a temporary variable s. But you need, after you get s, you need to update the value inside your dictionary. Non-f. You make it a known. You assign s to this corresponding element in the array. you make this Fibonacci number value known. Okay? Yeah. Yeah. It's positive number, so make it known. Yeah. After that, you can return. Okay? So you return because you will find the value, so you return it. But when you return it, your dictionary is updated, right? You update your dictionary. Yeah. All right? Yeah. So here you can see when you make your dictionary, yeah, because your dictionary at the beginning, all the slots are empty, but you keep adding numbers, yeah, Fibonacci numbers into your dictionary, filling those, yeah, I run out of time, I will finish quickly, yeah. So you fill all those empty slots with Fibonacci numbers, yeah, so you build up your dictionary, but at the same time, you find the value of the current Fibonacci number. But each number, you make sure you only calculate it once. So this is the main idea of dynamic programming. Very valuable. Okay? Yeah. So here, last sentence, yeah, before I finish today. So last sentence, yeah. Later, after you learn this class, yeah. So later when you work, yeah, so in your real world software development, when you have a chance to implement recursive algorithms, yeah, yeah, keep in mind you can use the idea of dynamic programming to help you reduce or eliminate redundant calculation, yeah, using this dictionary method. Okay, so you need to build up your dictionary and use it to avoid redundancy. Okay, all right, so that's it. So let me stop right here. Okay, all right. So I will complete the remaining 4 questions in your homework assignment number 1. So you can study the video, hopefully, so you can find good solutions. Yeah. All right, so that's it.